In 1859, the Victorian landowner Thomas Austin imported 12 wild rabbits into Australia and let them loose to breed. Since they had no natural enemies, the population increased very rapidly. By 1949, there were approximately 600 million rabbits. A. Find an exponential function using a continuous growth rate to model this situation. B. If the growth had gone unchecked, what would have been the rabbit population in 2000? Well, for part A, the first thing that we'll need to do is to recall the natural exponential model. The natural exponential model is A of t is equal to a sub 0 times e raised to the kt, where a sub 0 is the initial quantity, and the absolute value of k is either the growth or the decay rate, depending on whether k is positive or k is negative. Since a sub 0 represents the initial amount when time is equal to 0, what we'll want to do is to let time equal 0 correspond to 1859, which is when the rabbits were released into the wild. So let's first of all organize the information that's given in a table. In the year 1859, 12 wild rabbits were released. We'll let 1859 correspond with time is equal to 0. By 1949, the rabbit population had reached about 600 million. So what we need to do is to determine how many years past 1859 is 1949. So we just subtract 1949 minus 1859. That's a period of 90 years. Then in part B, we want to determine what the rabbit population would have been in the year 2000 if growth had gone unchecked. So we need to determine how many years past 1859 is the year 2000. We find that that's 141 years later. To find our exponential function, we'll need to determine the values of a sub 0 and k. Well, we can see from our table that a sub 0 is equal to 12. We'll need to figure out the value of k. And the way that we can do that is by substituting the ordered pair 90, 600 million into the formula. To solve for k, we first of all divide both sides of the equation by 12. The resulting equation is 50 million is equal to e raised to the 90k. Since k is in the exponent of e, our next step is to take the natural logarithm of both sides. The resulting equation is the natural logarithm of 50 million is equal to 90k. Finally, we divide both sides by 90 to get k. We find that k is the natural logarithm of 50 million divided by 90. We use our calculator to evaluate this expression. We find that k is approximately 0.1970. We substitute this value of k into the natural exponential model to get our exponential function. So the exponential function that models this situation is a of t is equal to 12 times e to the 0.1970 t. To complete part B, we simply substitute 141 for t into our function. In other words, find a of 141. We use our calculator to evaluate 12 times e raised to the 0.1970 times 141. We find that the rabbit population would have been approximately 1.389 times 10 to the 13th power. Writing this in standard notation, we get approximately 13 trillion 890 billion rabbits.